Alright, greetings everyone. Thank you for joining the hackathon. This is a small little tutorial on running the TransformerLens library to easily analyze activations in language models and also do some ablations and do a lot of the tasks that is super relevant for our mechanistic interpretability research this weekend. So I can click on all of these, I can click open in Colab, and we'll get the Colab notebook. And this is the main demo that you'll find on the GitHub page for the TransformerLens library as well. And in this case, we are starting with a bit of setup. This notebook was not authored by Google, but it is of course safe anyways. And this is relatively unimportant, but it just checks if we are running it locally on the computer in a Jupyter notebook or here on Colab. And for anyone who hasn't used Google Colab, it's basically a very useful way to intermix text and code and the code's output. So you can see that whenever we run something, we'll get all the output, as in this case where it says that the requirements are already satisfied. And this is setting up the plotting, which is just a library for plotting. And this is setting up CircuitsViz, which is a very useful library for plotting attention patterns in transformers. And this is importing a lot of the libraries that are going to support the TransformerLens functioning. So Torch, for example, is quite important, and that is PyTorch, one of the most popular. I think it's the second or first most popular machine learning library. And we also have transformers from Hugging Face, which has a bunch of helper functions for using transformers, for example, installing transformers from their website, their transformers website. And then of course TransformerLens, where we import these four functions along with these root module and point. So the hook transformer is a super method of, or a super class of the PyTorch model, and allows us to use these transformers with some hooks from the TransformerLens library. And we turn this off just to save some GPU memory. We have some helper functions for the plotting. And this introduction is basically the same as you'll find on the page for the TransformerLens. So this is the GitHub page and this text here. And it's about how Neil basically made this library as an open source tool for making mechanistic interpretability much easier after he quit Anthropic, where he was frustrated that there wasn't anything open that he could use, because we of course assume that Anthropic has some very good libraries within the organization. Yes. And one of the very useful sort of small things is that we have a bunch of helper functions for loading and running models. So this little line just asks if we're running on a machine with a GPU or not. And if we are not, we use the CPU. If we are, we use CUDA, which is just a different name for like something that interfaces with the GPU. So it's a compiler, but that's not super important. It just goes much faster if we use CUDA versus CPU. And this model, we take it from the hook transformer from pre-trained. So this from pre-trained function is super useful for loading one of the 40 plus different models that are in the TransformerLens library. And the device is just the device here. So in this case, that's CUDA. And here we can just try out if the model works. And what we've used is the GP2 small, which is an 80 million parameter model, but we have over 40 different open source GPT style models. Another basic operation we want to use when you're doing mechanistic interpretability is to break open the black box and figuring out what is happening when we run it, right? So in this case, we do that by saying model run with cache on the text. So tokens is the text, and the cache is the cache of what has happened, like what is the activations that have happened on this piece of text. In this case, we've run it here, so model to tokens. So the model has a function to like convert this piece of text to actual tokens, which is a bit different from actual text, but it's just like splitting it up and making it usable for the model to look at. And then we can have the GPT-2 logit and GPT-2 cache, which we get by running with cache. And then we can use the CircuitsViz library from Alan Cooney to basically visualize these. Bada bing. There we are. And this is just layer 0 so this is layer 0, but it has all these 12 different heads. And the attention heads of transformers is a very useful target for analysis, simply because they contain quite a good abstraction of the actual functioning of the network. So we often use that in our analyses of algorithms that the neural network learns. For example, in this case, we might see that head 4 in this case has, when I hover over comprehension, we can see that it attends to translation and maybe even a bit of machine translation as a second order effect. And this is probably because, you know, translation and comprehension are quite related. And otherwise, we don't have super many other patterns where maybe we can find another one that has an interesting pattern. Like head 6 maybe. Well, head 6 has summarization and comprehension, which it thinks are related. So the heads basically are information movers. They move information from part of the sentence to another. And this can be in different ways, but you know, if comprehension appears, then maybe that means that summarization will end with isation, which is quite useful to know. And now, another really useful function are the hooks. And this is one of the great things about neural networks is that we have full control over our system, which we definitely don't in neuroscience. So we can check and we can do surgical edits. And one of the very important things in science is to, well, one of the optimal things in science is to get a counterfactual of what has happened, you know. So can we get a baseline, a control group, can we get an experimental group? And in this case, we can just simulate that by running counterfactuals and doing causal interventions on the neural network. And what this means is that we can, for example, replace the activations of one head that we assume might be related to our algorithm. And we can say, okay, we assume this is related to our algorithm in the way that it changes or it finishes summa with risation if there's comprehension earlier, something like that. That's probably a relatively bad example, but there'll be one further down. And if we then, you know, remove that specific head's activations in one way or another, or replace them with something random, then maybe we won't get risation after summer. So then maybe we'll get, I don't necessarily know, summer season in a new dialect of English. But again, maybe a bad example. We'll look at that a bit more. So we will ablate head 7 in layer 0 on the text above, the one that we ran the other stuff on. And we define this head ablation hook. So ablation is exactly just like replacing the activations of a head with something. Either it can be the average of all the activations, it can be 0, it can be sampled from random distribution, which is usually the way we want to go, because that better simulates, you know, what would a normal attention head actually do. It would actually have real activations and not like weird activations like averages or 0. So that's what we do, and we can see that the ablated loss in this case is much higher, and the higher a loss is, the worse the model performs. So the original loss is lower than the ablated loss, meaning we've removed some information that was quite useful for it to get a good score. Yes. And one thing we can use this ablation stuff for is doing activation patching. And in this case, we are using the example of the indirect object identification task. And this is from a paper called Interpretability in the Wild from Redwood Research, where they basically study after John and Mary went to the store, Mary gave a bottle of milk too, and it should of course finish it with John instead of Mary. And then we want to, so this is called indirect object identification, where the indirect object is John, and identification is of course figuring out the object itself. And this task is super useful because it's a relatively simple algorithm that we can test in a bunch of different ways. So activation patching is then a technique from the wonderful Rome paper, and this is a technique used to identify which model activations are most important for completing a task, in this case, the indirect object identification task. So we have these two different prompts here, the clean prompt and the corrupted prompt, and we have two different answers. So we have the correct answer of John, and we have the incorrect answer of Mary. You'll also notice oftentimes that there's a space in front of these words, which you might think is weird, but that's because tokens usually are with spaces in front. So this is a token, basically. And they'll usually not be without that space because it's quite useful. So we basically measure what is the difference in expectation for the model to see John versus Mary on this text. That was a little model. Or a little alarm. I've become corrupted. But the clean prompt is this, so that we'll get the correct answer of John, and the corrupted prompt is John, so we'll get the incorrect answer of Mary. And if we run it, we can see that the clean logic difference between getting John or Mary is positive. So that means that when we take the expectation of getting John, which might be a high logit, right, like 5 or something, or it might be 3, and then subtract the incorrect answers logit expectation. So logit is this probability of selecting that token as the next token, and Mary might be minus 1 or 2 or something. Then we'll get the logit difference of 4, and vice versa. If the correct answer is, it might be 1, and the incorrect answer is Mary, but that'll definitely happen in the corrupted prompt, then we'll get a negative logit difference, which just shows that Mary is more probable in this case. And not necessarily, it's not an incorrect answer for the corrupted prompt, right? So we just get the difference. Now we set up a hook function to do the activation patching, and we'll patch in the residual stream, which is a term for for sort of where the information travels through in the transformer. And there is a link here for more information on that. It's a part of the architecture of a transformer. And in this case, that might take a short while, so I'll just pause it real quick. All right, here again, we are done now. So now we can visualize the results, and we can see that the information basically stays at Mary all the way through. And then only at layer 8 and 9 is the information transferred over to the end to be used for next token prediction. And in this case, the ablation is done at the beginning of the residual stream at that layer. So this layer 8 is actually layer 7, and layer 9 is layer 8. So we have layer 8, 9, 10. Yes. And with hooks, we can also just use them to access an activation. So to run some function on that activation value without changing the activation value, we can just have it return nothing, which means it's not editing the activation at all. In this case, we'll demonstrate this usefulness of extracting these activations for a specific task by running it on induction heads in GPT-2 Small. In this case, we are showing that we are generating, we're creating an induction head basically, and we then have 50 tokens before the sentence is repeated. So in this case, we can see that this is the loss by position on random repeated tokens. So all of these have a really high loss because the induction head doesn't know what to do with it. While then at the 50th position, because it begins repeating the sentence that happened here, up towards the 100 tokens, right? 100 words or whatever you want to call it, we'll see a much lower loss because it's much better at predicting, because induction heads basically train to copy information. So they'll be ascending from the second occurrence of each token to the token after its first occurrence. So that's 49 different, or a 49 token difference. And now we can then calculate an induction score for each head, like how much does it reduce in loss when you, or how much does it attend to a token 49 positions back. And we can see that head 1 in layer 5, head 5, head 9 in layer 6, and so on, have very high activation towards these things. So we'll take head 5 in layer 5, and we will use that again to run, to see the activation pattern. And we can see this is random tokens again, right? But we have 50, and then it repeats suddenly. So you'll see that its attention pattern, if we just hover over all the words, all the tokens here, will constantly be on phase. But when we then go to the next phase, it'll begin attending to the word that comes right after in the previous 50 tokens. So you can see that this is sort of the correlation matrix between the tokens, right? So the in and out and the attention pattern there. Relatively logical, but basically this head just, repeats what it saw before. And now going on to something a bit different. This is looking at the available models. So TransformerLens comes with these over 40 different open source models available. And the open source models are, they are documented below actually, both the open source models, but also the interpretability friendly models that he has trained, along with a set of toy language models. So these are tiny 1 to 4 layer models, and a set of solo models. So these are softmax linear unit models, which are very useful for ensuring a privileged basis. And this table goes to a link that does not work, but I have found it here in TransformerLens/TransformerLens/model properties table. And this has all of the names of the models that you can import. And you can see the parameters, amount of layers, amount of heads, and so on, all the way through. So the Pythia ones here, the Eleuther AI, Pythia, the Solus. So these are the ones that he has trained. So you have the old, I assume he would want to have you use the newer ones that don't have the old on it. And attention only, so these are the toy models, right? Wonderful. And they are all available. So here we can run again. We can load Distill GPT-2, which is a GPT-2 with half as many layers, and run this sort of induction head score on it, and see that we get some other heads that have this score now. Yeah, and here's an overview of the models themselves. So the open source models, you have GPT-2, of course, which is the classic generative pre-trained model from OpenAI. You have GPT-Neo. So Eleuther AI has both GPT-Neo, Eleuther AI both has GPT-Neo, GPT-X, and GPT-Neo-X. So this is a 20 billion parameter model, this is a 6 billion parameter model, and these Neo models, they are these sizes. And then OPT, you have Metas models, and you have the Stanford CRFM models, and you also have the Pythia models, which are, as mentioned, they are documented right here. So you have all of these Pythia models, which are also from Eleuther AI and that team, still a beta man, and so on. Yes. And here's another overview, and you can check it out more in depth yourself, along with some of the other resources here, the Transformer architecture itself and how it's set up, the features and other features from the library. So for example, dealing with tokens, as I mentioned, tokens are like the splitting. So you can see you have end of text, the first thing you need, and you can see the space again. So this is a text that is split up in tokens. So this library also makes it quite easy to do this. And factored matrix class. Yeah, so this is a way to analyze low-rank factorized matrices, which might become important for you. You can generate text, so you can model, generate, and then it'll generate the next line of text, right? So President Obama caught an embarrassing new scandal, and CNN reported Wednesday that the former president was charged with lying, blah, blah, blah. So this is standard functioning and hook points. So, this lets us access and edit intermediate activations using these hook points around every model activation with toy examples, and loading pre-trained checkpoints. So these are a way to, so the checkpoints are generally just models that during training are saved as well. So you get like models that are halfway trained and stuff like this. So this was the short little introduction to Neil Nanda's TransformerLens library, and we have all of these other contributors as well, but Neil Nanda started it. So a wonderful library for exactly this sort of mechanistic interpretability, and I'm excited to hear what you have of ideas and what the final product will be, along with any questions you might have that you can of course just ask on the server. So thank you very much, and check out some of the other resources on the page as well.